Organic molecules are based on the element carbon. Every organic molecule has at least one carbon atom. Okay, so carbon has 4 valence electrons, and those 4 valence electrons can be shared with other atoms. Okay, for example, it could be shared with the valence electron of hydrogen, and then that sharing of the electron forms a covalent bond. You do that with 4 different hydrogen atoms, and you form a molecule of methane, right? But of course, hydrogen is not the only element that can share an electron with carbon. There are essentially any element that has a valence electron to share can share share that electron with the carbon. So, for example, we can have a carbon-oxygen bond, because oxygen has 6 valence electrons. So there's one that it can share with the carbon. It could share the other one with the same carbon to form a double bond. Okay, that would look kind of like this, where I would have then those 2 available for sharing with some other element. Or it could form a single bond, and this could be shared with, say, another carbon atom, or perhaps a hydrogen, or something else. Okay, so and then of course not only oxygen but carbon itself is also a good candidate for sharing those electrons to form a bond. And so what we find is that carbon can form these chains. Okay, and each one, each dot here is an electron waiting to be shared with something. Quite often it's hydrogen, right? So you could share that electron with hydrogen, so that together they have 2 electrons, and then you do that with all of those, and that begins to look like a typical organic molecule. Okay, organic molecules often have a lot of hydrogen in them, and a good bit of oxygen is not uncommon as well. All right, so you'll notice that each carbon atom has 4 bonds, 1 bond for each of those unpaired electrons. Okay, and here's the case, we still have 4 bonds, even though one is a double bond. That's counting 2 bonds because it's sharing 2 of those electrons, and so a bond for each electron in its valence shell. And these are a couple of organic molecules. All right, but the key property of carbon that gives such a diversity of organic molecules is this ability to chain itself together. Okay, now you might be thinking, well, why can't silicon do the same? And the fact is, yes, silicon can form these bonds. However, it doesn't do so very often. More common is the silicon-oxygen bond. Okay, that's what quartz is, or glass, or many different minerals are formed from this silicon-oxygen bond. Right, and the reason that it doesn't form many silicon-silicon bonds to itself has to do with the energy of these bonds. Okay, a silicon-silicon bond is about 222 kilojoules per mole. That's how much energy is required to break that bond. Right? A silicon-oxygen bond, on the other hand, is 452 kilojoules per mole. So quite a lot stronger, in fact, over twice as strong as the silicon-silicon bond. Now, oxygen is very prevalent in our atmosphere, and that means that if you had a bunch of silicon-silicon bonds and they come in with an oxygen molecule nearby, it won't take a lot for that silicon to form a bond with the oxygen, because this is such an easy bond to break in comparison to the energy that would be released from forming that bond. Okay, when a bond is formed, it releases energy, whereas when a bond is broken, it absorbs that energy. It requires this energy in order to break that bond, but when it forms, it gives off that energy. And so it only requires a small amount to break that silicon-silicon bond, whereas it releases a large amount of energy when the oxygen bonds with the silicon. Okay? Now, if we compare that with the bonding in carbon, the carbon single bond is about 346 kilojoules per mole. Okay, and compare that with the carbon-oxygen single bond, which is about 358 kilojoules per mole. Right? So very close in energy. Right? It's slightly stronger, but it's not so much of an advantage over having a single bond to get that oxygen bond. It gives off a little bit more energy to form that bond than the single bond, but not a whole lot more. Right? And so that is part of the reason why carbon forms chains, but silicon, although it does form chains, you can get silicon in that form, but you have to be careful because it will react very easily with any available oxygen. All right, so that is kind of the background. If you look at the energy of those bonds, you begin to see why it forms compounds the way it does. And you can also look, the carbon-hydrogen bond is 411 kilojoules per mole. So it's even stronger than the carbon-oxygen bond, but still relatively comparable. All of those being in the same range gives it a lot of flexibility to make a wide variety of different compounds.